The frequency response of an n-order causal FIR filter is given in this equation, h exponent j omega equal to the summation from n equal to 0 until n of signal hn multiplied with the exponent negative j omega n. And the design of an FIR filter involves finding the coefficients hn that results in a frequency response that satisfies a given filter specifications. FIR filters have two important advantages over IIR filters. First, they are guaranteed to be stable even after the filter coefficients have been quantized, and second, they may be easily constrained to have linear phase. In practice, FIR filters are employed in filtering problems where there is a requirement for a linear phase characteristic within the passband of the filter. If there is no requirement for a linear phase characteristic, either an IIR or an FIR filter may be employed. Because FIR filters are generally designed to have linear phase, in the following we consider the design of linear phase FIR filters. The design procedures are based on the filter characteristic, where the first one is constraints on the magnitude and or phase of the filter response of magnitude hd exponent j omega. The second one is constraints on the filter step response, for example, the transition region from low to high or high to low. The third one is constraints on the impulse response HDN on the filter, and the fourth one is filter order N. So after the specification have been defined, the set of filter coefficients suitable for the impulse response HN is determined. So for ideal impulse response, suppose a low pass filter is being designed having cutoff frequency omega c. The derivation of filter specification can be begin by defining an ideal frequency response with linear phase and cutoff frequency omega c and its respective ideal impulse response. So for the ideal impulse response, it is equal to exponent negative j omega for frequency equal or lower than the cutoff frequency in this region, and it is equal to 0 for frequency larger than omega c and lower or equal to pi. Using the Fourier transform, the ideal impulse response can be determined using this equation, which is equal to 2fc, the cutoff frequency, sine omega cn divided by omega cn, which is also equal to sine omega cn divided by pi n, where omega cn is equal to pi n.